And thanks, Paulo, for the very nice introduction. I will share my screen now. So, good afternoon to everyone. Today I'm going to talk a little bit about spatial temporal modeling and in particular about the Brazilian wildfires. This is a joint work with two colleagues from Brazil. Rodrigo is my colleague at Federal University of Bahia, and Jonathan is a colleague that is doing the PhD at Federal University of Pernambuco. I had here a slide to introduce myself, but Paul already mentioned all of that. The only thing that Paul didn't mention is that now I'm a visiting professor at Monash University in Melbourne, Australia. So I'm going to stay here for the next 6 months approximately. So let me tell you what I'm going to talk today. This is the outline of my talk. I will start with some introduction about wildfires and how the Brazilian territory is divided. Then I will show all the data that we collect, some spatial and temporal data visualization. Then I'm going to present the model that we used and some results on spatial temporal modeling, and then some concluding remarks. So wildfires are very common in many places, including in Portugal, in Brazil as well, the south of the United States, in Australia, etc. So they are too common, and they do a lot of damage in terms of environment and public health. So in this particular study, what we considered was all the fire spots that were detected by satellite images in the Brazilian territory between the 1st of January of 2011 and 31st of December 2022. So this represents about 2.2 million fire spots. By fire spot, it is so this data is coming from satellite images, and there is a reference satellite that passes over Brazil every day, once per day, and it collects images, and based on those images, they are detecting the fire spots. Fire spots are, like you can imagine, like a kind of pixel in the picture. Okay, so we collect all of that data, we organize it, and this is the number of fire spots that were detected in these 12 years. Then after a spatial temporal visualization with some plots and some descriptive ideas, we did a spatial temporal modeling where we used the spatial temporal generalized linear model for aerial unit data, and the inference on the parameters were done based on a Bayesian approach. We consider the number of fire spots as a response variable, and we used also 5 covariates to try to explain that amount of fire spots. So we use 4 meteorological variables: precipitation, air temperature, humidity, and wind speed. And then we also use a human-based variable that is related with land use, transition, and occupation. So I'm going to talk a little bit about those variables in a moment. In Brazil, it is a very large territory, as everyone knows. Is the 5th in terms of area, and it includes 6 biomes. We have the Amazonia, that everyone knows, that it represents about 60% of the Amazonian rainforest, is located in Brazil. There is Caatinga, which is a semi-arid climate. There is Cerrado, which is a savanna. There is Mata Atlântica, that is more located in the Brazilian coast. Pampas, which is in the south, and there is this rainy climate. And there is Pantanal, that is a floodplain in Brazil. This is where they are located. The green on the top left is the Amazonian. The orange is the Cerrado. The yellow is Caatinga. Then the green is the Mata Atlântica. The south, the Pampa is the blue. And the Pantanal is the red right here. So what we have there, we have the Brazilian map. These solid lines, black solid lines that you can see are the divisions between states. Brazil has 27 states. And then you might see some small white lines there. Those are the divisions between municipalities. Brazil has 5,570 municipalities, so we have all the divisions there. Those dots that we have there, you see a lot of dots. These dots are the locations of the environmental stations that we use for this study. So are the locations where we collect the data for the meteorological variables like wind speed, the rainfall, etc. Okay. The data. So we use three databases. One was based on satellite images that was transformed in the number of fire spots per day per municipality. So what we did was imagine we transformed this data in a matrix in which you have the rows of the matrix are the days between the beginning of 2011 and the end of 2022, and the columns are the municipalities, the 5,570 municipalities. So essentially, each cell has the number of fire spots in that day in that municipality. Okay, so this is one data set that we use. The second one is the climate data, which are those environmental variables like wind speed, radiation, rainfall, and the other. And this is hourly, which means that we have measures each hour. And then the third one is related with land use and land use occupation. It is possible to measure from year to year what is the amount of land that moved from green areas to agro something, to plant some soja, for instance, or something like that. So we can measure that, and we use that as a third database as well. So this is what we did. We have here each of those columns is one of the data sets, and in the rows we have data collection, data treatment, and data organization. So the first column is number of fire spots. We did data aggregation per day. We had to input missing values as 0 because we assume that if the number of fire spots is not observed, it means that there are 0 fire spots in that day in that municipality. And then we got the total number of fire spots per day and per month, and we stratify them by biome and by municipality. Okay. The second column is the climate data. The climate data, we did data extrapolation. We had to go to get the data from municipalities. For instance, if I go back here, you see that there are some municipalities here that do not have any meteorological station. So what we did was that we assumed that there is some kind of homogeneity. And for instance, if I have a municipality here which do not have an environmental station, we did the average between the three that were closest to that station. So essentially, if there is this municipality here where I have the mouse, we did the average between that, and that, the three that were closest. and we did it in a weight form. So the one that is closest gains a higher weight. So a weight based on the inverse of the distance to the central point of the municipality. So that's what we did for the climate data, because we need the climate data for each municipality. And of course, we transform it from hour to day and to month as well. And then the last one is land use. So land use had a different problem because it was measured per year. So we did some kind of interpolation and some transformation from to consider it as thousands of hectares. And then we had three main variables. One is the gain and loss of green area, gain and loss of farming, and land use transition from green area to farming per municipality. So this is the one that we considered, the land use transition from green areas to farming for each municipality. Okay, so those are the variables. This is the data. And then we did some data visualization and some spatial temporal modeling. So this is how the number of fire spots look like. These are total amounts. These are daily data. So we can see that there is a clear seasonality in this data. And here in this table, I have the first column is the year. The second column is the number of fire spots in that year, which is measured in hundreds of thousands. And then the variation rate. So essentially this 37, it means that from 2011 to 2012, there was an increase in 37% of the number of fire spots, then a decrease of 41%, and so on. Here is the same kind of plot, but for each of the 6 biomes, we can see also the seasonality in each of them. And of course, you have to pay attention to the values in the axis, because Amazonian, it goes up to 33,000 per day, whereas this Pampas, for instance, which has a low incidence of fire spots, goes to 60 at most. Okay, so but all of them show very clear seasonality, maybe Pampas a little bit less. Here is a different kind of visualization. I have here the years from 2011 to 2022. Each map corresponds to 1 year. And what we did, the colors, the yellow, it means a lower number of fire spots. The dark red, a high number of fire spots. So we paint each of the 5,570 municipalities, and we were trying to look for some kind of trends. So we see that there are some locations in the map that are more red, which indicates a higher incidence of fire spots. So there are some years like 2017, 2022, 2019 that seem to have a higher incidence of fire spots. This is similar, but we did it per month. So essentially the January is the sum or the average, if you will, of the fire spots of all Januaries. February is the average or the total of all Februaries. March is the sum of all Marches, okay, for the 12 years that we are considering. So we can see the seasonality that we saw in the temporal map, in the temporal plot. We can see it here as well. So we see that August, September, and October are the months that have a higher number of fire spots. Here is just an example for one of the meteorological variables, in this case, relative air humidity. We can see that in Amazonia, there is a clear seasonal kind of data. It is also visible seasonal in Cerrado, in Pantanal. In Pampa, there is less than the others. There is a little bit of seasonality, but not as clear, and some kind of intermediate in Caatinga and Mata Atlântica. So this is how this meteorological variable looks like. Then this is the one that I want to tell you about, land use transition. So Land use transition, what I have here is I have a comparison between two following years. For instance, the first map here is the comparison between 2011 and 2012. And what it means is that if it is green, it means that we are gaining green area. If it is orange or red, it means that we are losing green area to farming. Okay, so it means that the more the map is red, the the more land we lost from green areas to farming. Okay, so we can see that some plots are worse than others. We can see that from 15 to 16 there is a lot of red, also 16 to 17, 20 to 21 there is a lot of red, especially in here the Amazonian and Pantanal. So this is more or less what this looks like. This one is similar, but we are comparing with a reference year. We are comparing all of them with 2011. So the first one is the transition from green areas to farming from 2011 to 2012. Again, red and orange means an increase in terms of farming. Green, light and dark green means a gain in terms of green areas. Of course, it is cumulative, which means that last one is more red than the others, of course, because this is cumulative. The last one compares 11 to 21. Okay, so this is how this data looks like in terms of visualization. And then we did a spatial temporal modeling. So the main idea here was to model the total number of fire spots aggregate per municipality and month. So we did not consider the daily data, we considered monthly data, and we include explanatory variables, the ones that I mentioned before: precipitation, temperature, humidity, radiation, and land use transition from green areas to farming. Okay? So these are counts. We are counting. The response variable is a count variable. So because of that, we use a spatial-temporal generalized linear model for areal unit data, and the inference on the parameters were made using a Bayesian framework. So the model that we used is the one that is described in this paper in Journal of Statistical Software. The name of the package is CAR-BASE-ST. This was published in this journal, and the package works quite well. So this is how the model looks like. So we have a Poisson distribution because we are counting the number of fire spots, and then these are the details about the priors, and here are the details about the parameters. I'm not going into much detail on this, but if anyone is interested in this, we can share either the reference or some of the information that we have in our paper. And these are the results. I have here 6 tables. One for what we did was, since there are a little bit of differences between the biomes, we did one modeling for each of the biomes. So the first table is for Amazonia, the second is for Caatinga, Cerrado, then on second column, Mata Atlântica, Pampas, and Pantanal. What I'd like you to look at is to this that I just highlight. So these are the variables that were selected. So we did a backward selection. We considered first the 5 covariates in the model, and then we start to remove them until we get only significant variables. So what I have here in the first column are the model parameters. Then we have the mean for the parameters, and then we have the credible intervals with 95%. So you can see that in this case here, for instance, land use transition, there is a positive coefficient, and the credible interval is also positive. For humidity, there is a negative coefficient, and a negative credible interval. So this means that the number of fire spots is positively influenced by the land use transition and negatively influenced by the humidity, meaning that a high humidity reduces the number of fire spots, which is what we expect. And that is, I think, a good conclusion of this work is that the land use transition from green areas to farming increases the number of fire spots. So, and this is for Amazonian. For the other biomes, it is similar. So land use transition was always significant and positive, which means that influences positively the number of fire spots. And then humidity was negative for all of them except for Pampas, where the precipitation was the variable that was more significant, also with a negative coefficient, meaning that higher precipitation results in a lower number of fire spots. So the conclusions for the environmental variables are as expected. The conclusion about land use transition from green areas to farming is something that we were not expecting. We could think of that, but it was not as clear for us. So these are some conclusions. The number of fire spots in Brazil is increasing. It has increased in the last years. The most affected biomes are those that are mostly on the news: Amazonian, Cerrado, and Pantanal. Mostly Amazonian, Pantanal. In the last few years, Pantanal burned a lot. The highest incidence of fire spots is August, September, and October. And then there is a loss in land use and occupation by green areas. This loss is going from green areas to farming and agro business. In terms of the spatial temporal modeling, the land use transition from green areas to farming was significant in this model that we considered, with positive coefficients, meaning that a high transition from green areas to farming influences the number of fire spots positively, and the precipitation for Pampas and the humidity for the other biomes had a negative coefficient, meaning that it influenced negatively the number of fire spots. So those were the main conclusions here in this work. I'd like to do some advertising about our lab, our statistical learning laboratory. So we have here in the bottom the link for that if you are interested. We have 7 directions here, 7 research directions. We have deep learning and artificial intelligence. We have big data, sports analytics, machine learning, time series forecasting, spatial temporal modeling, which is the one that this work is related, and statistical genetics. And in the bottom are the colleagues that are leading those research lines. So in this particular work, the collaborators are Rodrigo, that is leading this research line, and Jonathan. Jonathan is leading this machine learning. He is very good in terms of data cleaning and data organization and all which has to data organization is great with that. These are the 2 main references that we have here. The first one is the package and the model that we considered here, and second one is this paper, which is submitted. It has been submitted for longer than we thought. It has been submitted for half a year already, and we are still waiting for a response. Then those are my contacts, my email, my website, the link for the laboratory, and then the link for the laboratory in the LinkedIn and Instagram. And thank you very much for your attention.